Okay, in today's lecture, we're going to finish the section 1.9 material on the matrix of a linear transformation. And in the last part of this section, we're going to introduce some terminology related to transforms and see that for linear transforms, we have special properties that are related to this new terminology. So to start, let's introduce this new terminology. We'll start with some definitions. So first, let's suppose that we have a mapping T from Rn to Rm. This mapping is said to be onto if for each vector b in Rm, this vector b is the image of at least one x in Rn, the domain of my transformation. So that is, we say the transformation T maps Rn onto Rm, or it's called an onto mapping, if for each b in the codomain Rm, there exists at least one solution of the equation T of x is equal to b. That is, if for every vector b in the codomain, we can think of it as the image of some vector in the domain, then that mapping is onto. So the first time you see this definition, it might seem a little bit tricky, but let's try to visualize what exactly an onto mapping is. So visually, let's say that we have a space Rn, and we have a transformation T with Rn as its domain, and it's mapping into the codomain Rm. So this mapping is considered to be onto if every single vector b in Rm, so let's look at one of them, let's maybe call this b1, can be considered as the image of a vector x in the domain. So let's say for a given vector b1 over here, b1 is the image of some vector x1 in the domain. That is, T of x1 is equal to b1. And if we can do this for every vector in the codomain, so let's say for any choice, maybe if I choose another vector, b2, I can think of b2 as the image of some vector x2, so that T of x2 is equal to b2. Then this is an example of an onto mapping. That is, if I hit every single vector in the codomain as the image of some vector in the domain, then it is an onto mapping. So what would an example of a mapping which is not onto look like? Well, let's consider this. A mapping T is not onto if there exists some vector b in the codomain for which the equation T of x equals to b has no solution. That is, if there's some vector in the codomain which is not the image of any vector in the domain. So visually, let's say we have our spaces Rn, and T is mapping Rn into Rm. Well, for some vectors, let's say b1 in Rm, there are solutions of the equation T of x is equal to that vector. So some vectors I will hit in the codomain, but if there exists some vector, or let's say that I have this for two such vectors, so the image of x1 is b1, the image of x2 is b2, but let's say that I have some vector, maybe I'll call it b3, and there is no vector in the domain Rn which maps to b3. So here t of any vector x can never be equal to B3. This would be an example of a mapping which is not onto. Because there is some vector, B3 in this case, in the codomain, which is not the image of any vector in the domain. Now, another term which we have for mappings is the following. A mapping or transformation T from Rn to Rm is said to be a one-to-one mapping if for each B in the codomain Rm, we can consider that B as the image of at most one vector x in the domain Rn. So here, the difference is that T, between onto and one-to-one, is that T is one-to-one if for each B in the codomain, the equation T of x equals to B has either a unique solution or no solution. So let's try to visualize this here. Let's suppose that we have a domain Rn, which is mapped by T into a codomain Rm. And let's say that we have vectors, maybe B1 or B2 in the codomain, where each of these vectors is the image of some of at most some vector, or at most one vector in the domain. So here we could have something like this. This would be an example of a one-to-one mapping where each of these vectors in the codomain, namely B1, B2, or B3, is the image of at most one vector in the domain. So here, the only vector which maps to B1 would be the vector x1. The only vector which maps to B2 would be the vector x2, and we might have some vectors in the codomain, such as B3, which are not mapped to by any vector in the domain. So this would be an example of a one-to-one mapping. This is also the same example we have for a mapping which was not onto. So this is an example of a one-to-one mapping which is not onto. So what would it mean for a mapping to not be one-to-one? We would say that a mapping T is not one-to-one if there is some vector B in the codomain, which is the image of more than one vector x in the domain. So let's say that we have our domain Rn, which is mapped by T into Rm. Then let's say that we have some vector B1 which has two different vectors in the domain with that as its image. So let's say we have two different vectors, x1 and x2, which both map to the same vector B1 in the codomain. And maybe I have some other vector B2 which I don't hit at all. So this would be an example of a mapping which is not one-to-one, because the vector B1 has two different vectors with B1 as its image. So intuitively, a map is one-to-one if no two vectors map onto the same, or if no two vectors in the domain have the same image. All right. So we're often interested in determining whether a given mapping is one-to-one or onto, because these types of mappings have some nice properties. So we have the following two theorems, which will allow us to determine whether a mapping is one-to-one or onto. So the first of these theorems, Theorem 11, from your textbook, says if we have a mapping T from Rn to Rm, and this is a linear mapping or linear transformation, then that transformation is one-to-one if and only if the equation T of x equals the zero vector has only the trivial solution where x is equal to 0. So let's see if we can establish the proof of this theorem. This one's not too difficult to prove. So let's start by saying since T is linear, we saw from the previous section 1.8 that for a linear mapping, T of 0 has to equal 0. That is, the image of the 0 vector is the 0 vector. Now if the mapping T is one-to-one, then the equation T of x equals to 0 has at most one solution. That is the definition of a one-to-one mapping, is that if we have a specific vector in the codomain, say the 0 vector, it has at most one vector with that as its image. So if we have at most one solution, and we've already established that the 0 vector is a solution of that equation, then we know that is the only solution. So here, the 0 vector is the only solution. So we've established a one direction for this theorem. If T is one-to-one, then the equation T of x equals to 0 only has the trivial solution. Now we also need to establish the reverse direction of this theorem. That is, if T of x equals 0 only has the trivial solution, then the mapping T must be one-to-one. So let's prove that by using a contrapositive statement. So let's say the following. If the mapping T is not one-to-one, then that means there is some vector B in the codomain Rm that is the image of two distinct vectors. So let's say, for instance, U and V, where T of U and T of V are both have the same image, say B. Now, since T is linear, we know that T of U minus V is equal to T of U minus T of V. But since T of U and T of V were equal to each other, they both had B as an image, the difference leaves us with a 0 vector. So we have now shown that the equation T of x equals to 0 has a non-zero solution of u minus v. Since u and v were distinct vectors, their difference, u minus v, is a non-zero vector, and t of that vector was equal to the zero vector. So we've shown that if t is not 1-to-1, there must exist a non-zero solution of that equation. So equivalently, if t of x equals 0 has only the trivial solution, then t must be 1-to-1. So we have established the result for Theorem 11. Now in Theorem 12, we have another condition for whether a mapping is 1-to-1 or onto. So let's suppose that we have a mapping T from Rn to Rm, which is a linear transformation. And if it's linear, then we can find a standard matrix A for that transformation. So there's two parts to this theorem. The first part is that T maps Rn onto Rm, so in other words, T is an onto mapping, if and only if the columns of the standard matrix A for that transformation span all of the codomain Rm. And part two of this theorem is that T is a 1-to-1 mapping if and only if the columns of the standard matrix A are linearly independent. Okay, so let's establish the proof of this theorem. This one's not too difficult. It follows directly by definition in some earlier results from this chapter. So to establish part A, let's recall a result that we saw in one of our earlier sections. So recall from section 1.4 that the columns of a matrix A span all of Rm if and only if for each vector B in the codomain Rm, the equation T of x, which would be matrix transformation A times x equals to B, has a solution. So that's exactly what it means for the columns of A to span all of Rm, is that for every vector in Rm, the equation A times x equals to B has a solution. But this is exactly the definition of a onto mapping. Let's recall here that this says, okay, for each B in the codomain, B is the image of some vector x. That is, that equation is consistent. It has a solution. So we can say that is if and only if, T is onto. So those statements are equivalent. T is onto if and only if the columns of A span Rm. Now for part B of this theorem, so for part B of this theorem, we have T is 1-to-1 if and only if the columns of A are linearly independent. So recall from the theorem that we just proved, Theorem 11, we know that T is 1-to-1 if and only if the equation, t of x, which would be given by a times x equals 0, has only the trivial solution. But recall that this is the exact definition of linear independence of the columns of A. So this matrix equation, A times x equals to 0, can be written in vector form as x1 times the first column of A plus x2 times the second column of A, and so on. And if that matrix equation has only the trivial solution, that means the only way that this linear combination is equal to 0 is if each of these weights is 0. And that was the exact definition of linear independence. So we can say that is if and only if the columns of the matrix A are linearly independent. So we now have some conditions for testing whether a given transformation, which would namely be a linear transformation, so which could be expressed as a matrix transformation, whether it is one-to-one or onto. So in our last example, let's consider a specific transformation. So here T is a transformation from R3. So we're taking a vector with 3 components, and we're getting a vector with 2 components. So we're mapping from space onto the plane, R2, using the transformation T, which has the following definition. So for this matrix, or for this transformation, we're supposed to first find the standard matrix for that transformation. Now recall, to find a standard matrix for a transformation, we need to look at the image of the standard basis vectors. In this case, for the 3x3 identity matrix. So if we look at T of E1, now E1 is the vector 1, 0, 0, we would have as our image 1, 0. For T of E2, which is the vector 0, 1, 0, we would have for our image, let's see, -5, 1. And for E3, which is the vector 0, 0, 1, we have an image of 4, -6. So by theorem 10 from this section, the standard matrix for this transformation is the matrix that has these images as its columns. So my first column is 1, 0, second column is -5, 1, and my third column is 4, -6. All right. So this is the standard matrix for that linear transformation. And once I have this matrix, I can use theorems 11 and 12 to determine whether this transformation is one-to-one or onto. So in part B of this example, we are asked to determine whether the transformation T is one-to-one and justify our answer. Now we know from theorem 11 that this transformation is one-to-one if the equation T of x equals to 0 has only the trivial solution. And since this is a matrix transformation, T of x is equivalent to A times x. We want to set that equal to 0 and see if we have a solution other than the trivial solution. So this system that we're considering, or this matrix equation, A times x equals to 0, defines a homogeneous linear system whose augmented matrix is given by 1, -5, 4, 0, 1, -6. And since this is homogeneous, we're augmenting with the 0 vector on the right-hand side. So to simplify this, we could take row 1 and add 5 times row 2. And we have 1, 0, -26, 0, and 0, 1, -6, 0. So my matrix, or my augmented matrix, in reduced row echelon form, does not have a pivot in every column, which means that there exists a free variable. So here, x3 is a free variable. And we saw from our section 1.5 material that if there exists a free variable for a homogeneous linear system, there is a non-trivial solution. So here x3 is a free variable and a non-trivial solution exists. So by theorem 11, T is not a 1-to-1. All right. Now, equivalently, we could have made use of theorem 12 to get this result. So here, if we think about the columns of the matrix A, let's look at these. So our columns of this matrix A are the following 3 columns. So we have, we want to ask, are those columns linearly independent? Theorem 12 says that T is 1-to-1 if and only if the columns are linearly independent. But we see here that we have a set of 3 vectors of length 2. So from our section 1.7 results, we know if we have a collection of more vectors than the length of those vectors, then they cannot be linearly independent. And therefore, theorem 12 says that this transformation could not be 1-to-1. So that's another approach we could use there. Now, in the last part of this example, we are asked to determine whether the transformation T maps R3 onto R2. So is this an onto mapping? So making use of the theorem 12, part A, we know that this mapping would be onto if and only if the columns of A span all of R2. So let's say the following by theorem 12, T is onto if and only if the columns of a span all of R2. But if we recall from one of our earlier sections, the columns of A will span all of R2, provided there is no row in the augmented matrix without a pivot. Since we see from our augmented matrix that we had looked at in part B, we have a pivot position in every row, we can say, or since there is no such row in A, the transformation T is an onto transformation. So it is onto, but it is not one-to-one. There are multiple vectors. So we hit every vector in R2 with this transformation, but there are vectors in R2 which have different vectors in R3 as the image or with the same image. So here, this example illustrates by making use of theorems 11 or 12, we can determine from looking at the matrix A for a linear transformation whether that transformation is one-to-one or onto.